Okay, so find this page of your notes. You should have gone through all the patterns. If you didn't, that's okay. Should be on page 3 in your notes packet. Okay, today we're comparing linear, quadratic, and exponential patterns. You should be pretty familiar with linear and exponential patterns, and maybe know quadratic a bit. Some of you may have seen quadratic already. So I start by what their graphs look like. Okay, a linear graph. Linear graph is just a line. Okay, so we're going to graph f of x equals x, which is the parent function of a linear equation. So our pattern is just going to have a slope of 1 and a y-intercept of 0. So this is the graph of y equals x. It goes to the origin. It has a slope of 1. It goes up 1 over 1. It's linear because the graph is a line. Okay, it has an equation. The recursive equation is f of x equals the previous term, which is f of x minus 1, plus a common difference, what it keeps adding over and over again. It's like the slope. We know the slope to be m. So you're adding something over and over again. Repeated addition. Okay. The explicit formula, you would know this more as the slope-intercept form of a line. Y equals mx plus b. So f of x equals, remember m is the slope, b is the y-intercept. Okay, your ordered pairs. In this case of our graph, when x is 1, the y is also 1. When x is 2, y is also 2. When x is 3, y is 3. When x is 4, y is 4. When x is 5, y is 5. Okay, you can see what you're adding over and over again by looking for the first difference. What did I have to do to the 1 to get to 2? I add 1. What did I do to the 2 to get to 3? Add 1. 3 to get 4. Okay. This is a constant rate of change, okay, which means this is a linear because you're adding 1 over and over again. And this is also the slope. The slope would be 1. Okay. Any questions over that? Okay, so a linear function always is just increasing by the same number. It can increase by 5. It can decrease by 2. It can increase by a half. Okay, but it's always going to, over and over again, be adding the same number or subtracting the same number. Does that make sense? Any idea on what has a linear pattern in real life? Yes. Age. Okay, you're getting older every year. Very good. Okay. Anything else?
My looks, I'm still old.
Well, that wouldn't be a constant rated, right? You won't be changing, right? It'd be Flat, right? Yep.
School.
School, what does that mean?
We're in the school every minute of our lives.
Nope, that's not true, right?
Feels like it.
Oh, it may feel like it, but it's not true. Okay, what about hourly wage? Would that be a constant rate of change? Could you constantly be adding those hours up? Okay, unless you're getting paid overtime, it's going to be a constant rate of change. I get paid $15 an hour, so you're going to make $15 every hour, and it's not going to change. Okay, so that would be hourly wage. Okay, profits and sales. Okay, you're going to make the same profit every time you sell that same product over and over again. Probably last year you had some word problems involving selling something, and what was the outcome? What was your profits? Okay, those are linear. Those are constant rates of change. Okay, now we're going to go to exponential. And exponential is f of x equals whatever number you want to the x power. I'm going to use 2 because it's easy to graph. When you get bigger numbers, it becomes more difficult to graph because you need a big old graph. Okay, and you had exponential growth last year as well, and exponential decay. So in this case, when x is 0, 2 to the 0 power is 1. When x is 1, 2 to the first power is 2. When x is 2, 2 squared is 4. When x is 3, 3 cubed is 8. Okay. And if you did -1, it would be 1/2. 2 to the -1 is 1/2. 2 to the -2 is 1/4. Is it ever going to touch that x-axis? No, it's going to approach it, get really close to it, but never touch it. If you remember that from last year. Okay. The x-axis would be an asymptote for f of x to the 2x power. 2 to the x power, sorry. So it starts off really slow, and then it just skyrockets in the growth. Any questions over that? So that's exponential. So the recursive formula is f of x equals the previous term. And in exponential functions, we are repeated multiplication. We're multiplying over and over again. So it's times the common ratio. In this case, it was 2. It's repeated multiplication. Any questions over that? Okay, the explicit formula is f of x equals b to the x power. The b is the base. In this case, we did 2. But it could be 1/2, it could be 3, it could be 5. Any questions over that? Okay, then our ordered pairs. Okay, for the graph that I used, when x was 1, y was 2. When x was 2, y was 4. When x was 3, y was 8. When x is 4, it's going to be 16. And when x is 5, it's going to be 32. So you can notice here that what I'm doing to the 2 to get to 4 is I'm multiplying by 2, or timesing by 2. Then from 4 to 8, again, I'm timesing by 2. 8 to 16, I'm timesing by 2. 16 to 32, I'm timesing by 2. Any questions over that? Let's make my 8 look more like an 8. Any questions over that? Okay, do we know of anything in real life that has exponential pattern? What kind of word problems did you guys do that had exponents, exponential stuff? Yeah?
Like in a cab, like you have like the jump in it and then how many miles.
That would be like a constant because the mile per mile, right? Every mile would be a linear. You might start with a flat fee and then linear. Exponential is if it doubled every mile. So after mile 1, now it's doubling, and mile 2, it's doubling again. And that'd be like you'd be ending up paying like a ton of money after a very short ride. So, stocks don't necessarily have exponential growth. You could maybe compounding interest is considered exponential. You should have bacterial growth. Let's spell better. Growth or decay. You talk about half-life, certain bacteria having a half-life. Okay. So if you put one bacteria, it'll multiply very quickly. Cell reproduction is also exponential because they grow a cell, then that grows a cell, and then it keeps more and more and more. Okay, those are where we see them in real life. Okay, our last one is our new one. Okay, it is quadratic. You might not be as familiar with this. We have f of x equals x squared. Okay, so you would go where x is 0, 0, 0. And when x is 1, y is 1, because 1 squared is 1. When x is negative 1, negative 1 squared is also 1. When x is 2, 2 squared is 4. When x is negative 2, negative 2 squared is also 4. When x is 3, 3 squared is 9, so it'd be up here. Negative 3 squared is also 9, so it'd be here. So here's my quadratic function. It is what we call a parabola. Is this familiar to you guys at all? Yeah? Okay, good. Okay, you don't really have a recursive formula, or we have one. We're just not going to deal with it this year. Okay, you're going to see more recursive in linear and exponential than you will in quadratic. The explicit formula, though, would be f of x equals ax, ax squared plus bx plus c. That's standard form of a quadratic. Okay, then our ordered pairs, when x is 1, y was 1. When x was 2, y was 4. When x is 3, y was 9. When x is 4, y was 16. When x is 5, it was 25. So now we would look at our first difference. What did I do to the 1 to get to 4? I added what? 3. What did I do to the 4 to get to 9? I added 5. What did I do to the 9 to get to 16? And what did I do to the 16 to get to 25? Let's see. Okay, that's our first difference. And unlike our linear pattern, it wasn't the same. And unlike our exponential, we weren't multiplying by something over and over again. Okay, we were adding a pattern, right? 3, 5, 7, 9. What would be the next one then? I'd add 11. Okay. So then we go on to our second difference. This is our first difference. And it doesn't match like our linear did. So now we're going to go from here. What did I do to 3 to get to the 5? I added 2. What did I get to add to the 5 to get to 7? Added 2. And 7 to get to 9, I added 2. This is my second difference. Okay, and those all match, and that's exactly how the pattern is going to work. Your first difference won't match. It'll be in a pattern. Okay? Very similar to this one. 3, 5, 7, 9, 11, 13, 15. Okay, adding odd numbers. Okay, the second difference, though, should all match. And that's how you can tell it's a quadratic. If it doesn't match, then it's not going to be quadratic. It might be something else that we haven't learned yet. Any questions? Okay, quadratic patterns. Anyone know of a quadratic pattern? Football players, you see this all the time. A field goal. Okay, when you kick a field goal. Okay, that pattern of the football is going to be quadratic. Golf, when you hit a golf ball. Okay, when you throw a baseball. Okay, all of those are quadratic patterns. When you launch a missile, okay, quadratic pattern, and you want to be very accurate. So those are all things that you will see an exponential pattern. Any questions? Okay, you don't have this next page in your notes because I made a mistake. So you're going to go flip to the back, the last page in your notes. It's a blank page. And you're just going to write it here. So write down A in those ordered pairs for me. Write down that table for A. Still working? Okay, then it says to find the first and second difference of the following quadratic functions. So our first, between 12 and 7. What I have to do to 12 to get to 7? Subtract 5. From 7 to get to 4? Subtract 3. From 4 to get to 3? Subtract 1. From 3 to get to 4, I add 1. From 4 to get to 7, I added 3. From 7 to get to 12, I added 5. Okay. Again, that was all a pattern. 5, 3, 1, 1, 3, 5. Okay. Now we want to see if the second difference matches. So negative 5 to negative 3, I had to add 2. From negative 3 to negative 1, again, I added 2. From negative 1 to 1, I added 2. From 1 to 3, I added 2. And from 3 to 5, I added 2. So my second difference did match. Any questions over that? Okay, let's go to the next one. Write down the equation and the table for me. Okay, and then I'm plug this in. I'm going to have f. I'm going to plug in negative 3 to start with. Negative 3, f of negative 3 equals negative 3 minus 1 squared. F of negative 3 equals negative 3, negative 1 is negative 4. I squared negative 4, and I get 16. Then I'm going to plug in negative 2. So f of negative 2 equals negative 2 minus 1, the whole thing squared. This becomes f of negative 2. Negative 2 and negative 1 is negative 3. Negative 3 squared is 9. Any negative number squared is going to become positive. Okay, then plug in negative 1. F of negative 1 equals negative 1 minus 1 squared. F of negative 1. Negative 1 and negative 1, same sign I'm going to add and get negative 2. Negative 2 squared is 4. I'm going to plug in 0. F of 0 equals 0 minus 1, the whole thing squared. 0 minus 1 is negative 1. Negative 1 squared is 1. Then I'm going to plug in 1. Okay, I ran out of room, so I'm just going to plug it in. 1 minus 1 is 0. 0 squared is 0. Then I plug in 2. 2 minus 1 is 1. 1 squared is 1. 3, I plug in 3. 3 minus 1 is 2. 2 squared is 4. Okay, first and second difference. What did I do to 16 to get to 9? Subtract 7. 9 to get to 4. Subtract 5. 4 to get to 1. Subtract 3. 1 to get to 0. Subtract 1. 0 to get to 1. Add 1. 1 to get to 4. Add 3. Okay, again, they don't match. Okay, so we go on to our second difference. What I do to negative 7 to get to negative 5, I added 2. 5 to get to negative 3, added 2 again. Negative 3 to get to 1, I added 2. Negative 1 to get to 1, add 2. And 1 to get to 3, I added 2. Any questions over that? Okay, I want you guys to answer these two questions. What did you notice about all the tables of values? What patterns do you see? And what conclusions can we make about quadratic patterns as a result of the observation? What do we notice here? Write down some of the patterns you see. Answer those two questions. What do you notice about all the above tables? You can answer it in the form of a question. I noticed that all the table of values had this. Okay, Ashley, what did you notice? Yeah, very similar, right? The pattern of 1, 3, 5, 7, 9, 11. They have negatives though too. Negative 7, negative 5, negative 3. Go down, back down to 1. Okay, and then all the second differences were all 2. Okay. Megan, what did you notice?
I said that they all have like different signs.
Okay. Yep. So these are all quadratic because they have that patterned rate of change. And the first and second difference, the second different matches is all the same number. Anything else we noticed about their ordered pairs? Did we notice anything about all the f of x values or the y values? That's kind of different than linear. Anyone else have anything else they want to add? Do you guys notice that the y values can repeat? So especially here on A, 12 and 12, 7, 4, and then 3 didn't repeat, but all the other x or y values repeated here. 16, 9, then 4, 1, 0, then 1 and 4 repeated. Okay. And that'll happen. Any questions over that? Okay, so your homework.